So now that we've talked a bit about the Java Completable Futures framework, which I mentioned is which is an asynchronous programming model, and we've talked a little bit about the reactive programming concepts and principles, let's take a step back and think more fundamentally about synchrony first and then asynchrony. Now we'll start out by talking about synchrony, and we'll discuss what it is and what its pros and cons are. As we've alluded to earlier, method calls in typical Java programs, and for that matter, typical C++ programs or typical C# programs or typical Python programs, pick your favorite programming language you are using these days, are largely synchronous. So think about, for example, making calls on a Java collection. So you've got an array list, you want to add something to it. You've got a map, you want to put something in it, you want to take something from it. Those are examples of calls that are synchronous. Likewise, behaviors in your typical Java stream aggregate operations, where you're applying a bunch of behaviors or applying a behavior to a bunch of elements in a stream using map, also done synchronously by default. The basic idea here is that the callee borrows the thread of control of its caller until the computation is finished. And here's an example. You can see we're making these calls, and then the results come back. And so that's inherently request response. I'll run it again so you can see request response. And these are what we would call two-way synchronous calls. And most calls that you've dealt with up to this point in life are probably two-way synchronous calls. Now that we've given a quick overview of what synchrony means, let's talk about why it's good or when it's good. We'll talk first about the good things, and we'll talk about the bad things. So the good thing about synchronous calls is they're very intuitive to program and debug. And they're probably intuitive because that's what you've done pretty much from the beginning, unless you've spent a lot of time doing asynchronous JavaScript code, which most people probably haven't done. So they're intuitive, and that's because they map onto these very, very familiar two-way request response patterns. Nothing really surprising about that. Another reason they're intuitive and easy to program and debug is because the state of the local caller, the one that's making the call, is retained in the activation record of that particular method, so that when the callee returns, the state is sitting right where it was left. So there's nothing else you have to do to restore the state. It just happens magically because of the way that activation records work in stack-based programming languages, which are the vast majority of programming languages in use today. Here's a very simple example. This is a method called download content. And as you can see here, what it's going to do is it's going to create a local variable called buff, and a local variable called OS, and a local variable called IS, which are the representative types byte array output stream and input stream. And then it's going to go into a loop, and it's going to make a method call here to a read method and a write method, which of course will push those method calls onto the runtime stack to carry out the operation behavior of reading and writing, respectively. But notice how these local variables, including this bytes local variable, when read returns and write returns, bytes and buff and OS and IS all still have their same value as before. You are not responsible in any way, shape, or form for explicitly having to restore the state of that particular set of local variables when methods called by download content return. And if you're thinking to yourself, well, duh, that's exactly the point. That's the way you program probably most of your lives. So there's nothing surprising here, just saying local caller state is retained when the callee returns, and it's automatically reconstituted without you having to do anything special. There are, of course, some downsides to synchrony. As I'm very fond of saying, everything's not unicorns and rainbows. One of the problems, probably the main problem for the point of view of our discussion here, is that synchronous communication, synchronous computation, synchronous calls may or may not, probably may not, leverage all the parallelism that's inherently available in modern multi-core systems. So things aren't as speedy as they might otherwise be. Why is that? That's because blocking threads, when you make a method call and it blocks, that incurs overhead. It incurs the context switching overhead, synchronization overhead, data movement overhead, memory management costs, and so on. And so you might think that everything's going to be really nice and orderly and work well, but there's often a difference between theory and practice, where stuff ends up being more chaotic and you don't get things done when you expect, and so on and so forth. Another problem is that selecting the number of threads to use can be tricky and hard. So here's a very simple example. This comes from the image stream gang program, which is actually very similar to the parallel streams crawler that you wrote, where we take a list of URLs and then in parallel we get rid of the ones that are already downloaded and cached. We download the ones that are not cached. We apply filters to them and then we collect them up into a list. And as you can see here, this download image call is a blocking call. And that raises the very important question, how many threads do we need to have in our pool of threads in order for this code to parallelize efficiently? And the answer is it's surprisingly tricky to figure this out. You might end up spawning a large number of threads, which can improve performance, but then perhaps waste the resources you have if they're not used effectively. And likewise, we could also create a very small number of threads, which would use resources more effectively, but would end up impeding performance because we can't have as many things running in parallel as we might want. So this is particularly the case, this trade-off, trying to figure out the right answer here, is particularly tricky for I/O-bound programs that need more threads to run efficiently. And there's no good one answer here. As you're familiar, in parallel streams, we can use things like setting the number of threads as a property, which is kind of crufty and inflexible. More commonly, we would use the managed blocker interface, but even there, it's a little bit hard and you end up spawning a lot of threads. So how do we change the size of the common fork join pool? We talked about that, selecting a property or using managed blockers to basically create new threads as needed and then terminate them when they're no longer needed. But both of those approaches are a little bit crufty and complicated, and many programmers aren't familiar with how they work, although if they took my courses, they would know because we cover them in great detail. So that's the end of the quick overview of the pros and cons of Synchrony.